Saxon Algebra 1, Lesson 113. Welcome to week 3. We're going to talk about direct and inverse variations. This is a simple idea, and the only reason the math is simple, the formulas are simple. The only thing that trips students up sometimes and makes them feel confused is that we're going to be applying them to science ideas. I'll say more about that when we get there, but let me explain what variations are in a simpler way. Have you ever watched a group of toddlers playing? Kids that are old enough to walk, but not necessarily all that verbal, and they tend to play more by themselves than with other kids. That's really the biggest thing. I had a play group when my kids were little. There were about 7 or 8 kids that would come regularly. We all played in the same neighborhood. And when we were getting ready for play group, we would all kind of set out a lot of toys, so the kids would have lots to choose from and they wouldn't fight over sharing. And what was always interesting is that, toddlers just pull toys off shelves. They do not necessarily play for long. They just love to pull toys off shelves. So I could write a direct variation about that. I would say that the number of toys on the floor at the end of the play group, let's say I studied in my neighborhood, and what I found was that consistently there were 5 toys on the floor for every child that attended the play group. So T equals the number of toys, and C equals the number of children. Now, this number could change because maybe some of the kids were sick, or it was summer and a lot of the families were on vacation. Maybe instead of having the 7 or 8 kids that were normal, maybe I only had 3. But they still would get out 5 toys during the play group and throw them on the floor, right? So this number was a constant. No matter how many kids were there were always 5 times as many kids. The toys were always equal to 5 times the number of children. Now, let's go to a different neighborhood. Let's say this is a neighborhood where there are a lot of professional athletes living, and their children tend to be super energetic, super high energy, super into running around and grabbing and throwing things. At their neighborhood play groups, they may find that their kids get out a lot more toys. Again, it can vary with the number of children who are there, but their kids get out many more toys over the course of their play groups than mine. All right, let's go to a third neighborhood. Let's say that this neighborhood is full of people who study the Montessori method for training children to sit quietly and play with toys for long, extended periods of time. And neatly put them back on the shelf. So those children don't throw their toys on the floor. So at the end of their play groups, there may be only 2 toys per child that need to be picked up. So what I'm saying to you is that this constant may change in some scenarios as we go from one neighborhood to another, but within that particular neighborhood, that constant will stay the same, no matter whether there's a measles epidemic or everybody's on vacation or it's a nice day, so half the families have gone to the park and they don't come to playgroup, right? The number of kids may vary, but in these neighborhoods, under these conditions, the constant will stay the same. Now, I could also write, as part of my overall study of these children, that the number of toys on the floor is a direct variation of the number of children. This number, again, is a placeholder. I don't have a specific value in there, but that's me saying, hey, there's some constant, there's some number that's going to describe how many toys each kid throws on the floor in a play group. And this may be scientifically dubious, but I'm saying that it's consistent in the same neighborhood over time. So that's the idea with how a direct variation works. What John does is he amps this calculation up by giving us science applications. And so let's look at the kind of problems he's going to give us, which are a little more complicated than my toys and kids example. First, I want to show you this though. On page 474, don't write this down. I want you to see, though, that there are statements here. Ooh, they're scientific statements. The weight of a substance varies directly as the volume of the substance. Force varies directly as the current. The distance, I'm reading it in my fake sciencey smart voice. The distance traveled varies directly as time. And there's more on the next page. But see up there, there's a couple more. What John does is he shows you the exact equation that you need to know to calculate for that particular scenario. So I'm going to write down page 474. You can find there the scientific expressions that may be helpful to you in solving these problems, but I'm going to give you better advice. Sorry, John. Just follow the flow of the words. They will help you write out the equations. The number of toys on the floor after playgroup is directly varies with the number of children in the room. See how it goes toddlers to children? Just follow that. That will work. Again, we're talking about direct variations so far, right? I better write that here. Direct is just a little bit different. I mean, inverse. Okay, let's try a sciencey problem. Ready? Example 113.3. No, 0.1. What am I saying? Okay. This says the mass of a substance varies directly as the volume. The mass of a substance varies directly as a volume. As soon as I see the words varies directly, I know, oh, there's got to be a constant in there. This is the equation we'll use for our formula, or our scenario here. This, again, is the constant. Now, there are two steps to these problems, and let me just define those. In the first step, we're going to solve for k. We'll find the constant for this particular scenario. We're finding out how many toys the kids in this neighborhood throw on the floor. Then we'll use that constant with another set of information to answer the question, and that's part 2. Okay, so those are our steps. They'll always be the same. So in our first scenario of this problem, if the mass of 2 liters of the substance is 10 kilograms, that is confusing. If the mass, so we're talking about mass and volume, right? Mass is, on Earth, mass and weight are similar. So we would be looking for how much something weighs. Volume, the best way to understand volume is like by how we buy liquids, like liter bottles, 2-liter bottles, things like that. If the mass of 2 liters is 10 kilograms, that tells us that the volume is 2 liters and the mass is 10 kilograms. We can tell which is which because we match the units. The best way to think of liquid volume is liquids, and the best way to think of mass is weight. Mass is not exactly the same idea as weight, but on Earth, mass and weight are the same because gravity helps us. Okay, I don't need to get into a science thing. All right, so straightening out which one of these information pieces is the volume and which is the mass. We know that mass is like weight, so this kilograms is a weight, and volume is a way of measuring liquids. Liters, 2-liter bottle, that makes sense. Okay, so we can use this information to solve for k, but I'm going to write down the second part. What will be the volume of 35 kilograms? Okay, again, I know that kilograms must be the mass. We don't need the units to work the problem. We need the units to just help us sort out which is mass and which is volume. And again, that's where students can get frustrated. But trust me, just look at the units and it'll be fine. Okay, so we're going to start here by taking these numbers and plugging them in. 10 equals some mystery constant times the volume, which is 2. All we need is the numbers. We don't need the units anymore. Divide by 2 because we want to get that k by itself. And we find out that the constant is 5. Okay, so now we're ready to answer the question. We know the constant and we know one of the letters, so we can say 35, because that's m, equals 5 times the volume. We don't know what that is, so we'll just put in the v. And guess what? The numbers come out again super easy. Volume equals 7, and we don't have to think very hard. We just copy the units to our answer. The units are there simply to help us. They shouldn't scare us or hurt us at all. Okay, so there's our answer. That's correct. How about it? Next one. The distance traversed by a car traveling at a constant speed is directly proportional to the time spent traveling. So the distance traversed by a car at a constant speed is directly proportional to the time spent traveling. And then I squeeze the k in. I like the k before the second letter, so I would just leave a little gap there. How did I know that I could ignore all, how did I know I could ignore all those words? The distance traversed by a car traveling at a constant speed. That was a whole lot of words besides just D, but this is how I knew. The phrase is directly proportional. I knew that's where the equal sign goes. So is directly proportional helped me know that I was ready for my equal sign. This had a big, long, blah, blah, blah sentence, science word, science word, science word. I ignored them. I just looked for this, because that tells me where to put the equal sign, and then time was very simple on the other side. Okay, first step, I'm going to get information about D and T, and that will let me solve for K, and then once I do that, I'm going to get either D or T, and I will solve for the other one. So I know I can set these up every time. And sometimes I like to just put K right here so it's in the list. All right, if a car goes 75 kilometers, is that a distance or a time? Easy. In 5 hours, how far will it go in 7 hours? So the distance is the question. All right, let me read it again. The distance traversed by a car traveling at a constant speed, blah, 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 is directly proportional to the time spent traveling. There's the K. I could also look this up on the list on page 474, but I don't want to look it up on a list. I'd rather just listen to it. If the car goes 75 kilometers in 5 hours, how far will it go in 7 hours? See how the words just lead us in? All right, here I know that I'm using this. 75 equals K times 5. I plug in. I'm solving for K. And I get that K equals 15, right? I divided that in my head. 5 goes into 50 10 times, and that would leave me 50 minus from 75 leaves me 25. 5 goes into 25 5 times. That's how I did it. That might just confuse you, but sorry. All right, now I take this information and I plug back in. This is driving the whole thing. See how I'm going down in a column? Now I say distance equals K, 15, times the time, 7. Because I'm multiplying these, I went ahead and used parentheses around one of the factors to help me distinguish that. And now I get that the distance will be, let's see, can we do this in our heads? 7 times the 10 is 70. 7 times the 5 is 35. I add those together, 105. What's my unit for my distance? I look in the book. Car goes 75 kilometers, so it's kilometers. Guess what? It's the right answer. The math is easy, right? It's just making sense of the science situations. Okay, we have one more, and then we're going to switch to the indirects. I'm going to squeeze it in right here. Under certain conditions, the pressure of a gas varies directly as the temperature. Flow of the words. The pressure of the gas varies directly as the temperature. First scenario. When the pressure is 800 pascals. Ooh, I don't know what those are, but it's okay. The temperature is 400 kelvins. Oh, I know what kelvins are. They're a scientific temperature thing, but again, it doesn't matter. What is the temperature? So that's the question. When the pressure equals 400 pascals. And then I'll put room for K. I'm going to figure that out up here, and I'll put room for it down there. Now I can use this. I'm going to scooch my column over just a little, but I'm going to follow this flow. 800 equals K times 400. Beautiful. John's making these numbers so cute for us, isn't he? So K equals 2, right? This reduces, the zeros cancel. 8 over 4 is 2. Okay, I'm going to write that down here. And now I can write my second scenario. Again, I'm using this. P 400 equals K, which is 2, times T. And again, the numbers are just pure heaven, aren't they? This would be, I'll squeeze it right here. T equals 200, and now I have to find out what's the unit on my T variable. Oh yeah, T stands for temperature, and that's Kelvin, so I can just put a K there. It's confusing because this K stands for kelvins, but this K stands for the constant. If you wanted, you could write kelvins, just so your brain doesn't fry. But this is our answer. Yay! The math is cute, right? Inverse variations always remind me of teenage boys eating pizza, and girls too, for that matter. So let's not make it boys, let's make it both. I see that there's a relationship between the number of slices of pizza that are left in the boxes that I buy P equals the pizza slices, T equals the teenagers. The amount of pizza that I have disappears very quickly, and the more teenagers I have, the more pizza I'm gonna need, right? So this is an inverse relationship. This is teenagers eating pizza. The more pizza you have, the teenagers are gonna eat it, and the constant describes how quickly they're going to eat it. In my neighborhood, when all the teenagers get together, they may eat it really, really fast. In another neighborhood where everybody's allergic to glutens, students might eat at a much slower rate. But I can write this relationship for the inverse variation as this. I already wrote it once, but I'm writing it again. Right? We divide for an inverse variation because as one thing goes up, the other thing goes down. All right? So that's what we're going to work in these problems. They work exactly the same way. It's the same two-step. As you see the scenarios, even though they are all science-y again, you'll kind of get a feel for what's happening. Under certain conditions, the pressure of a perfect gas varies inversely. Now, as soon as I see that, I can write the K and make the fraction. It varies inversely as the volume. That's why when we hear them say it varies directly, we automatically know it's going to take this shape. As soon as we hear it varies inversely, we know it's going to take this shape. This one's pressure and volume, but any inverse relationship is going to go like that. Okay, so then we have our two scenarios. And we keep reading. When the pressure of a quantity of gas is 7 pascals, okay, I don't know what a pascal is, but they say pressure equals 7. The volume is 75 liters. What would be the volume, okay, so that's our question, if the pressure is increased to 15 pascals? Oh wait, yeah, that's right. I wrote them in opposite order, notice, just the way the story went. But that doesn't matter. We'll still plug them in this way. Let's go through it again. The pressure of a perfect gas varies inversely, so I know to put the K in the fraction line, with the volume, as the volume is technically what it says. When the pressure is 7, the volume is 75. What would be the volume, that's my question mark, if the pressure is 15? Beautiful. We're ready to go. Let's start by setting this up. Pressure 7 equals K over 75. Ooh, okay. So K equals, I multiply these two together, right? 7 times 75, let's do that over here. 35, 3, this is 49 plus 3 more is that. The constant in and of itself in these science problems will have no meaning to us. And it's okay, it doesn't need to have meaning to us. We just use it mathematically. Okay, so there's that. I copy it down here. Now I'm gonna set this up again, right? This is driving both calculations. Pressure is 15 equals the constant, 525, over the volume. We don't know what the volume is. So it's that. Huh. Okay. Well, how do we solve for V? What I want to do is cross multiply, and I'll get 15V equals 525, and then I'm going to divide away the 15 to solve. All right, we do have one more. I really hate to go to another page. So let's do 525 divided by 15. 15 times 3 is 45. I know that, so that's pretty good. 45, we subtract. Oh, okay. If 15 times 3 is 45, and I need 30 more, right, to get to this. So I know that 15 times 5 equals 75. I feel like we did that fairly recently. 25, 2, and I'm double checking my math here. 5 times 1 is 5, plus 2 is 7. Okay, it worked out. So that means my answer, the volume is 35. There's my answer. What's the unit? I don't know. Let's look back at our problem. The volume is 75 liters. I see written in the book. So I say, okay, this is a volume, so I'll just put liters on it. So you just go back and look for that same, the same category, right? Volume, not pressure. I look for volume in the problem, and then I look and see what unit they attach to that, and it's liters. If we were doing science at the same time right now, this would all make a lot more sense to us. But here's the thing, if I teach you how to do the math, then when you're in a science class and you get to these calculations, you're not gonna skip a beat. You're gonna understand exactly how to do this, and the other students will be looking at you and their mouths will be hanging open because you'll be like, yeah, this is fine. This is just an inverse variation. I know what to do. They're gonna be like, how did you know this? And you will say, talk to John Saxon. He taught me what I know. And then when you get home, you'll text me and say, oh my gosh, it happened in my science class today. You can even text me in class. I don't mind. 113.5, last one. Ready? To travel a fixed distance, rate is inversely proportional to the time required. Rate is inversely proportional to the time required. See how you can sort of see the equations start to jump out at you? We could ignore things like to travel a fixed distance. That's just putting limits on it that we don't care about. Rate is inversely proportional to the time required. There we go. Scenario 1, we'll get a rate and a time. Scenario 2, we'll get a new rate, a new time, and by then we'll have a constant. When the rate is 60 kilometers per hour, if you want, you can just jot it here so you have it. You don't have to look back at the book. The time required is 4 hours. So those are the units that match to those variables. What would be the time required? There's my question mark. For the same distance, okay, that's important for the science, but it doesn't affect us. If the rate were increased to 80 kilometers per hour. I'm not going to write the rates over again. I've got them up here, so I don't need to put the units again. I'm going to use this information to solve for K, and then I'll bring that down here and do this part. Now I just fill in 60 equals K over T, which is 4. I kind of like solving for K with inverse variations because you multiply those. So we get K equals 240. That's a big number, isn't it? I can put it right here. Now we do this again using these numbers. 80 equals 240 divided by T. All right, so again, we cross multiply. 80T equals 240, and we divide by 80. And we get that the time equals 3 hours. Did I get it right? Yes. Now, I want to say one thing to help you solve these. If you'll notice, when we have a scenario like this where we have the two numbers up top and the variables in the bottom, which you'll get fairly often, not every time, but you'll get fairly often in these problems, we can go through the steps of cross multiplying and then dividing away. But notice that what you get back to is basically these two guys change places. So if you're careful, you can kind of make that mental switch and go directly from this to this without the extra step of like mentally cross multiplying and then dividing away. You know that's where you're going to end up, so you can just kind of jump there. This is the right answer. And that is the end of lesson 113. Look, we're already into week 30. Yay! Thank you. Goodbye.